imagine a place in the universe where the laws of physics pack up their bags and leave. That is a black hole, a cosmic trapdoor where gravity wins every argument. If the universe were a game, a black hole would be the part of the board where all the rules stop making sense. Light, time, matter, energy, everything that dares to cross its boundary disappears from our universe's to-do list. It is not so much a place as it is an idea, one that sits at the edge of our understanding, taunting us with mystery. Now, black holes might sound like something from science fiction, but they are as real as the stars that gave birth to them. They are not cosmic vacuum cleaners roaming around space, gobbling up planets like intergalactic Pac-Men. Instead, they are perfectly still monsters, quiet, patient, and terrifyingly powerful. If the sun were replaced by a black hole of the same mass, Earth would continue orbiting just as it does now, cold, dark, and lonely, sure, but not sucked in. Black holes are less hungry beasts and more gravitational extremes, bending space-time itself into shapes that defy imagination. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. To understand just how wild that is, we need to talk about gravity's dark side. Normally, gravity is the reason your feet stay on the floor and why you cannot dunk like a basketball star. It is the gentle tug that keeps the planets in their lanes. But black holes are what happens when gravity stops being polite and starts getting real. Einstein's general theory of relativity showed that gravity is not a force in the traditional sense. It is the bending of space and time caused by mass. A planet curves space a little. A star curves it a lot. But a black hole curves space so much that it becomes a waterfall of geometry, and once you fall in, there is no climbing out. Picture this. Space-time is like a giant rubber sheet. Place a bowling ball on it. That is your sun. The sheet dips slightly, and marbles rolling nearby circle around it. That is the Earth orbiting. Now imagine pressing your thumb straight through that sheet. That hole that goes all the way down, no bottom in sight. That is a black hole. The bowling ball was a celestial body. The thumb hole is a gravitational catastrophe. What makes black holes even weirder is how they twist not only space, but also time. Near a black hole, time slows down. The closer you get, the slower it ticks. If you could hover near the edge, you would see the rest of the universe speed ahead. Stars forming and dying, galaxies colliding, eons passing in what feels like seconds. It is like watching the fast-forward version of existence while you remain in cosmic slow motion. And then there is the question that has kept scientists and storytellers awake for decades. What happens once you go past that invisible border, the event horizon? From the outside, we cannot see beyond it. No signal, no light, no information comes back. It is as if the universe drew a curtain and said, you do not get to know. Everything we can describe about black holes, their mass, spin, and electric charge, comes from the outside. The inside, that is the universe's best kept secret. The irony is that the concept of black holes started as a mathematical prank. When Einstein's equations were first published, they described how matter curves space-time. A few years later, a physicist named Carl Schwarzschild found a solution that implied a region of space where the curvature becomes infinite. At first, even Einstein thought it was nonsense, just a weird quirk of the math. But nature, as it turns out, has a sense of humor, because not only do black holes exist, they are common. Our galaxy alone likely hosts millions of them, from small ones formed by dying stars to giants lurking at the centers of galaxies, each with millions or billions of times the mass of the sun. So if black holes are so real, why can we not just point a telescope and see one? Because you cannot photograph darkness. What we can do is capture its outline, the silhouette it casts against the glowing gas swirling around it. In 2019, the world got its first glimpse of that shadow, the supermassive black hole in galaxy Messier 87. It looked like a fiery donut, the universe's most intimidating pastry. That image was not just a scientific triumph, it was a cosmic selfie of the universe's most secretive object. But the real fascination with black holes goes beyond their danger or mystery. They are nature's ultimate thought experiments. Every time we try to understand them, we end up learning something deeper about reality itself, how space and time behave, how information might survive destruction, and how our current theories might crumble under the weight of the unknown. Black holes are less like cosmic monsters and more like philosophical riddles wrapped in math. They are the places where our equations whisper, "I do not know." As we stare into the abyss, it stares right back, mostly because light cannot leave it anyway. But what it reflects in our minds is the frontier of curiosity itself. What really happens inside that gravitational trap? Is there another side? Do the rules of quantum mechanics find a way to survive? Or does reality itself get rewritten in there? Those are the questions we are about to chase, step by step, chapter by chapter. So, buckle up, because from here on out, we are not just learning about black holes, we are falling into one. Stars live fast and die dramatically. Some go out quietly, fading into cosmic retirement as white dwarfs, glowing embers of what they once were. Others, the truly massive ones, decide that if they are going to die, they might as well make it a show. These are the stars that end their lives not with a whisper, but with an explosion so bright it can outshine an entire galaxy for a short, glorious moment. And from that spectacular finale, if conditions are just right, a black hole is born. To understand how that happens, we need to peek inside the life of a star. A star is not just a ball of fire hanging in the void, it is a nuclear engine. Deep in its core, hydrogen atoms are constantly fusing into helium, releasing energy in the form of light and heat. That outward pressure of radiation pushes against gravity, which is always trying to squeeze the star smaller. This cosmic tug-of-war keeps the star stable for millions or billions of years. Think of it as a perfect balance between explode and implode, but that balance does not last forever. When a star runs out of hydrogen, it starts fusing heavier elements, helium, carbon, oxygen, and so on, until it eventually reaches iron. And iron is where the party stops. Fusing iron does not release energy, it consumes it. So when the core fills with iron, the outward pressure fades, and gravity, which has been patiently waiting its turn, finally gets the upper hand. Then, everything happens faster than you can say stellar meltdown. The core collapses under its own weight, the temperature skyrockets, and the outer layers rebound violently, blasting into space as a supernova, a cosmic explosion so intense that for a brief time it can radiate more energy than the sun will produce in its entire lifetime. What's left behind depends on how massive the original star was. A moderately large star might leave behind a neutron star, a dense ball of neutrons about the size of a city. But if the collapsing core is massive enough, even neutron pressure cannot stop the fall. The collapse continues past the point of no return until the matter is crushed into something so dense that it forms a black hole. That's the universe's version of cleaning up. Just throw it all into a black hole. Everything that once made up a shining star, its atoms, light, and heat, is now confined to a tiny region of infinite density, hidden behind an invisible curtain where physics itself folds in on itself. The transformation is violent, brief, and final. It's like watching the ultimate magic trick, except the magician doesn't just hide the rabbit. He hides reality. Now, not all black holes are born equal. The smallest ones, called stellar mass black holes, form from these dying stars. They usually weigh between 3 and a few dozen times the mass of our sun, but they are packed into a sphere only a few kilometers wide. Imagine cramming Mount Everest into a teaspoon, then realizing that teaspoon still has gravity strong enough to trap light. That's how absurdly dense these things are. Sometimes, when two massive stars live as a binary pair, they both can go supernova and leave behind black holes orbiting each other. Eventually, those two can merge, releasing a burst of gravitational waves, ripples in space-time that stretch and squeeze the universe itself. When the Laser Interferometer Gravitational Wave Observatory first detected those ripples in 2015, it was like hearing the universe's baseline for the first time. Two black holes colliding sent a cosmic boom across billions of light years, and we actually caught the echo. But black holes can also form through quieter, more mysterious means. Some scientists suspect that smaller ones, so-called primordial black holes, may have formed in the early universe, moments after the Big Bang. Back then, the cosmos was an incomprehensibly hot, dense soup of particles, and tiny fluctuations in density might have created pockets where gravity squeezed matter into miniature black holes. If any of those survived, they'd still be out there, drifting through space, perhaps smaller than an atom yet, with the mass of a mountain. The universe, apparently, has always had a thing for weirdness. The death of a star and the birth of a black hole are poetic opposites, a bright beginning giving way to perfect darkness. Yet this process is vital for the universe. The supernova explosions that accompany such deaths scatter heavy elements, carbon, oxygen, iron, into space, seeding future generations of stars, planets, and eventually life. So in a strange twist of fate, we owe our existence to the same cataclysms that create black holes. We are, in a sense, made from the ashes of dying stars that just barely avoided becoming cosmic singularities. When we look up at the night sky, we are seeing the middle-aged crowd of stars, the calm before the chaos. Somewhere out there, others are nearing the end of their fuel, their cores starting to tremble, their outer layers expanding. When they finally collapse, they will give birth to new black holes, fresh tears in the fabric of space-time. Some may quietly lurk in the void, others might wander through galaxies, invisible except for their gravitational pull. There's something both humbling and terrifying about that. The universe doesn't dramatize, it just follows its own rules, no matter how extreme the result. Black holes aren't accidents. They're the logical conclusion of too much mass and not enough resistance. In a way, they're nature's version of a full stop, a punctuation mark on a stellar story that ended with a bang. So next time you see a star twinkling in the sky, remember, it's not just a light, it's a nuclear balancing act, a performer in a cosmic play that could someday collapse into one of the most mysterious objects in existence. The universe doesn't waste anything, it just recycles in spectacular fashion. And when it's done, it sweeps the leftovers into the darkest corners of reality, its very own black hole housekeeping service. If the universe had a "do not enter" sign, it would hang right on the edge of a black hole. This invisible boundary is called the event horizon, a name that sounds poetic and calm, like something you'd watch the sunset over. But in reality, it's the most unforgiving border in existence. Cross it, and you're gone. Not metaphorically gone, not lost in space gone, physically erased from the visible universe. If black holes are cosmic prisons, the event horizon is the cell door slamming shut. Let's start by imagining what an event horizon actually is. It's not a physical surface, not some wall of matter or energy. You could drift across it without feeling a bump or a flash of light. One second you're out here, the next, you're in a region from which no signal, no photon, no radio wave, no desperate text message can ever escape. It's the line in space-time where the gravitational pull becomes so strong that all paths, even those of light, curve inward. The universe is effectively saying, all roads lead inward now. Good luck. The reason light can't escape has everything to do with how black holes bend space-time. According to Einstein's general theory of relativity, gravity isn't just a force pulling on objects, it's the warping of the very fabric of reality. Picture space-time as a stretchy fabric. Place something massive on it, a star, for instance, and the fabric dips slightly, light passing by curves around that dip, which we perceive as gravity. But a black hole isn't just a dip in the fabric, it's a bottomless pit. The curvature becomes so extreme that every possible path leads down. Imagine rolling a marble on a trampoline, except now the trampoline stretches into a funnel with no end. Once the marble reaches a certain point, there's no amount of energy or speed that could roll it back out. That point of no return? The event horizon. Now, the name itself, event horizon, comes from an interesting idea. In physics, an event is just something that happens at a particular place and time. The horizon part refers to the fact that, from outside, no events beyond this boundary can ever affect you. It's like the ultimate privacy setting of the universe. Whatever happens inside stays inside. You could throw a planet, a spaceship, or your least favorite celebrity past the horizon, and all you'd see is their light slowing, dimming, and freezing in time at the edge, forever stuck in slow motion. This illusion happens because of how time behaves near the event horizon. The closer you get, the slower time runs, at least from an outside observer's point of view. To someone watching from a safe distance, it looks like you never quite make it across the horizon. You just fade and freeze, redshifted into darkness. But from your own perspective, you'd glide right through, blissfully unaware that you've crossed the universe's most unbreakable border. In that sense, the event horizon is both a gateway and a mirror, depending on where you stand. And this is where things get truly weird, because from a physics standpoint, information shouldn't just disappear. Yet when something crosses the event horizon, it vanishes from our universe's record. Energy, matter, and light, all gone, like data deleted from existence. This used to drive physicists absolutely mad. If the universe is supposed to conserve information, where does that information go? Into the hole? Onto the surface? Or is it somehow smeared across the horizon itself? Some theories later suggested that the event horizon might actually encode everything that falls in, storing it like a cosmic hard drive. But for now, the details of that process are still murky, and we'll explore it much later. From a more visual perspective, the event horizon is what gives black holes their dramatic look. Remember that fiery donut image captured by the Event Horizon telescope? That bright ring isn't the black hole itself. It's the glowing gas and light swirling just outside the horizon. The black center is the shadow, the absence of light, where even photons have lost the battle. The horizon outlines that shadow, defining the visible edge of invisibility. If you were hovering nearby, you'd see light bending in wild circles around it, creating a distorted, almost psychedelic view of the universe. In a sense, the event horizon doesn't just trap light, it sculpts it, creating the most hauntingly beautiful optical illusion in the cosmos. And if you ever wondered what it would feel like to fall toward one, here's a hint. You wouldn't notice when you crossed the event horizon, but you'd know you were in trouble. Space-time itself would stretch, distances would lose meaning, and escape would become less of a hope and more of a punchline. If you cross it, you're not coming back. Kind of like replying to a group chat from 2012. You could fire rockets, scream into the void, or invent a new law of physics. It wouldn't matter. The geometry of the universe itself has turned against you. One of the strangest aspects of the event horizon is how absolute it is. There's no loophole, no escape clause. Even light, the fastest thing in existence, can't beat it. And yet the boundary isn't just a barrier, it's a storyteller. Everything we can possibly know about a black hole comes from what happens just outside it. The swirl of hot plasma, the bending of light, the distortion of time, all those clues let us reconstruct the shape and mass of something we can never truly see. The horizon hides the truth, but it also defines the mystery. In the end, the event horizon isn't just a cosmic no-entry sign. It's the edge of knowledge itself. Beyond it lies whatever remains when space, time, and matter give up their day jobs. To stare at a black hole's horizon is to stare at the limit of human comprehension, the border between what the universe allows us to know and what it keeps locked away. And that's what makes it so haunting. It's not just darkness. It's the promise that something lies beyond, something we may never be able to reach or understand. So as we drift closer to the edge, keep this in mind. The event horizon doesn't scream danger. It whispers curiosity. It's the quiet, invisible rim of the cosmic abyss, the last place light ever says goodbye. There are many unpleasant ways to die in the universe. Supernova blast, gamma ray burst, accidentally drifting into Jupiter's gravity well. But none quite compare to being pulled apart atom by a black hole. This is not poetic exaggeration. It is literal physics. The process even has a name so absurdly perfect that you might think scientists were in on the joke: spaghettification. It's what happens when you get too close to a black hole and gravity decides to turn you into an interstellar pasta noodle. To understand why this happens, we need to talk about tidal forces. On Earth, tides are caused by the moon's gravitational pull being slightly stronger on one side of the planet than the other. It's a gentle tug, just enough to move oceans around twice a day and ruin some beach picnics. Now, imagine cranking that same effect up to galactic proportions. Near a black hole, gravity isn't just strong, it's unreasonably strong. The difference in gravitational pull between your head and your feet can become so extreme that one end of your body is being dragged faster than the other. The result? You stretch. A lot. Until your molecules line up in a long, thin strand. Congratulations, you've just become the universe's most tragic noodle. The idea might sound cartoonish, but it's a deadly serious phenomenon. The strength of this stretching depends on the size of the black hole. For smaller ones, say a few times the mass of the Sun, the tidal forces near the event horizon are so intense that you'd be torn apart long before you ever crossed it. One moment you're bravely approaching the cosmic abyss, and the next, your atoms are being rearranged into a pattern Michelangelo might admire if he were into molecular art. But if the black hole is supermassive, like the ones sitting in the centers of galaxies, the story changes. The event horizon of a supermassive black hole is much farther from its center, and the gradient of gravity, the rate at which it increases, is actually gentler at that distance. In other words, for a truly colossal black hole, you could cross the event horizon without immediately feeling anything unusual. You wouldn't even know you were doomed until you were deep inside. Spaghettification would still happen, of course, but later, when you're much closer to the core, where gravity becomes lethal in ways that no human body could possibly survive. What's fascinating here is how cleanly physics can predict your demise. The mathematics behind it is mercilessly elegant. Gravity increases with proximity, and as the difference between the gravitational pull at your head and your feet grows, so does the tension on your body. First, your bones snap. Then, your muscles tear. Your molecules separate. Your atoms themselves start to distort. And eventually, you are stretched into a one-dimensional filament of particles spiraling helplessly toward the singularity. If Death by Black Hole had a Yelp review, it would definitely be 1 star. Yet, it's not all horror. There's beauty in the mechanics. Spaghettification is gravity revealing its rawest form, unfiltered and uncompromising. On Earth, we treat gravity as background noise, something we escape briefly in elevators or airplanes, but near a black hole, it becomes a sculptor, reshaping matter with relentless precision. Every particle of you is following its own curved path through warped space-time, and those paths diverge the closer you are to the singularity. It's geometry gone wild, the universe sketching spirals of destruction on an invisible canvas. If you could somehow observe this from a safe distance, which you can't because safe and black hole rarely belong in the same sentence, it would be a bizarre sight. As you fall, the light from behind you would warp, curve, and redshift. To an external observer, it would look as if you were slowing down, fading, and stretching endlessly toward the event horizon, an infinitely long noodle frozen in time. Of course, from your own perspective, things are quite different. You would experience your fall in real time, accelerating toward the center faster and faster, oblivious to the cosmic pasta making that the rest of the universe thinks is happening. This strange mismatch, your personal experience versus the outside view, is one of the most haunting features of relativity. From your vantage point, spaghettification is a quick, unstoppable plunge. From everyone else's, it's an eternal slow-motion stretch. The universe has turned your death into a physics lesson for any curious onlookers. But here's a delicious twist of irony. The very thing that destroys you could also help astronomers understand black holes better. The process of tidal disruption, when a star or a planet gets spaghettified, is visible from billions of light years away. As the object gets torn apart, it forms a swirling disk of superheated gas that emits intense X-rays and visible light. When telescopes catch such outbursts, they're witnessing cosmic spaghetti in progress. These events not only reveal the presence of otherwise invisible black holes, but also tell us about their size, spin, and appetite. In that sense, spaghettification is not just a violent end, it's also a spotlight. It illuminates the unseen. Every stretched atom, every scream of radiation becomes a beacon in the dark, letting us map where these gravitational monsters lurk. Even in its brutality, the universe is generous with information. Of course, if you're the one doing the falling, that philosophical comfort won't mean much. Your atoms might become part of the accretion disk, your energy radiating briefly before joining the black hole's mass. In a way, you'd achieve a strange kind of immortality. You'd become part of the cosmic equation, no longer an observer of the universe, but a participant in its most extreme form of recycling. Spaghettification might sound absurd, but it's one of the purest examples of gravity's power. It's what happens when mass and space-time work without mercy or moderation. No explosions, no sound, no theatrics, just an unstoppable stretch toward infinity, the quiet, graceful violence of physics in motion. So yes, being stretched thinner than linguini by a black hole isn't exactly an ideal vacation plan, but in that moment, if consciousness could somehow survive, it would be an awe-inspiring farewell. The last thing you'd ever see would be the entire universe distorted, twisted, and drawn into a tunnel of light, spiraling around you as you fall. Then, darkness. The final stage of the cosmic pasta process, served hot and gravitationally uncompromising. Time is one of those things we think we understand until the universe proves otherwise. We treat it like a river, steady, one-directional, predictable. You wake up, eat breakfast, scroll through your messages, and time moves on. But near a black hole, that river becomes a whirlpool. It bends, slows, and stretches until it no longer flows the same for everyone. In fact, if you were to fall toward a black hole, time itself would start playing tricks on you, tricks so strange that, depending on who's watching, your fall could last either seconds or eternity. This bizarre phenomenon is called time dilation, and it's one of the strangest consequences of Einstein's theory of relativity. In essence, gravity doesn't just bend space, it bends time too. The stronger the gravitational field, the slower time moves. On Earth, this effect is barely noticeable. A clock at sea level runs infinitesimally slower than one on top of a mountain, but the difference is so small you'd need atomic precision to detect it. Near a black hole, though, time dilation becomes less of a curiosity and more of a full-blown identity crisis. Let's set the scene. You're an adventurous astronaut, bravely drifting toward a black hole, while your equally curious friend stays behind at a safe distance. You both have synchronized watches. As you approach the black hole, your friend's view of you starts to change. To them, your motion slows. Your signals, your light, your radio messages start arriving more and more redshifted, stretched to longer wavelengths by the growing gravitational field. Your voice becomes lower, fainter, until it fades entirely. From your friend's perspective, you appear to freeze at the event horizon, never quite crossing it. You're just stuck there, suspended in time. Meanwhile, from your own perspective, things feel completely normal, at least until gravity starts doing unpleasant things to your anatomy. Your watch ticks along perfectly fine. Seconds feel like seconds. You don't feel time slowing down. In fact, you cross the event horizon without noticing anything unusual at all. And here's the cosmic punchline. While you're still alive and falling deeper, the entire universe outside of you races forward in fast motion. Galaxies spin, stars are born and die, civilizations rise and vanish. From your perspective, you're moving normally, but the rest of reality is sprinting ahead at breakneck speed. So, to the outside world, you never actually fall in. To you, you fall in instantly, and both are true. Welcome to the universe's ultimate optical illusion. Or as one physicist once put it, you die quickly, but we watch you die forever. Comforting, isn't it? This effect is so extreme that even light, the fastest traveler in the universe, can't escape its consequences. When light tries to climb out of a gravitational well, it loses energy, shifting toward redder colors. The deeper the well, the greater the redshift. Near a black hole, light emitted from just above the event horizon becomes so redshifted that it disappears entirely from view. To an outside observer, that's why objects falling into a black hole seem to fade, slow, and vanish before they ever reach the horizon. It's not that they stop, it's that their last photons are stretched into invisibility. In a way, black holes are cosmic time machines, but they don't send you backward or forward in the way science fiction imagines. Instead, they twist time into something subjective. Each observer gets their own timeline, and both timelines are real. Time becomes local, a personal experience rather than a universal rhythm. If that sounds confusing, that's because it is. Einstein once said that the distinction between past, present, and future is only a stubborn illusion. Near a black hole, that illusion breaks down completely. Now imagine standing far from the black hole, watching your brave friend fall in. You see their descent slow to a crawl. Maybe you record it, zoom in, try to catch the moment they disappear, but that moment never comes. They seem to hang there forever, glowing faintly, frozen on the edge of the abyss. From your perspective, they never actually cross the event horizon. The universe could end before they do, yet from their perspective, they've long since crossed it, their journey continuing into whatever lies beyond. It's one of those paradoxes that makes you realize how limited human intuition really is. The strange thing is, we've actually measured this kind of time dilation, not near black holes, but in more modest settings. Astronauts aboard the International Space Station experience a tiny bit of it. Because they're farther from Earth's gravity, their clocks tick slightly faster than ours. When they return home, they've aged a fraction of a second more than the people on Earth. Near a black hole, that difference wouldn't be a fraction of a second. It could be millions of years. You could, in theory, orbit close enough to a black hole that a few hours for you would correspond to centuries for the rest of the universe. It's the ultimate form of procrastination. Go near a black hole and skip the next 1,000 years of work. But this isn't just a cool trick. It's a window into how deeply space and time are intertwined. They aren't separate things, but part of one fabric, and gravity stretches both together. The deeper you fall, the slower your personal time runs relative to the universe outside. It's like being trapped in cosmic molasses, watching the rest of existence speed by. The poetic irony here is that black holes, which seem to destroy everything, also preserve something eternal, the moment of falling. From the outside, that moment never ends. You are forever there, frozen on the edge of infinity, caught in the act of crossing a line no one can see. If there were a museum of cosmic phenomena, your last frame would hang there forever. The caption reading, "Astronaut, circa 13.8 billion years, still buffering." So yes, time near a black hole doesn't just slow, it fractures, it bends, it rebels. To fall into one is to experience the strangest truth the universe has to offer, that time itself is not universal. It's a matter of perspective, and from where we're standing, watching the fall from a safe cosmic distance, you'll never quite disappear. You'll always be right there, frozen at the edge of eternity, a ghost of physics, forever mid-fall into the darkest mystery of all. There's something perversely human about wanting to know what's behind every locked door, and in the cosmos, no door is more tightly sealed than the one that leads inside a black hole. We can see its edge, the event horizon, glowing faintly in the light of crushed matter spiraling around it. We can even describe what happens up to that border with mathematical precision. But once you cross that line, once you step inside the abyss, the universe stops returning your calls. No telescope can look in, no signal can come out, and even our most trusted equations start muttering nonsense. It's as if reality itself shrugs and says, "I got nothing." Inside, physics stops making sense. It's like the universe's version of a 404 error, reality not found. The familiar rules, those neat, comforting laws that tell us how particles behave, how space curves, and how energy moves, collapse under the sheer weight of gravity. What remains is speculation, brilliant guesses, and math that works right up until it doesn't. To venture past the event horizon, even in theory, is to dive into a world where logic is optional and paradox is the native language. Let's start with what we think might happen. Once you're past the event horizon, you can't hover or pause. There's only one direction left: down. Down, of course, doesn't really mean anything anymore, because space itself is warped. Every direction points inward, toward what physicists call the singularity. It's the heart of the black hole, the place where all the mass is supposedly crushed into an infinitely small point. Imagine taking an entire star, millions of kilometers across, and squeezing it until it has no size at all, but still contains all its mass. The math says it's possible. The brain says, "That's ridiculous." Both are right. At the singularity, the density becomes infinite, the curvature of space-time infinite, and the word infinite itself starts to lose meaning. It's the cosmic equivalent of dividing by zero, an operation that produces not a number, but a problem. Every equation we have, Einstein's relativity, quantum mechanics, thermodynamics, throws up its hands and walks out of the room. The singularity isn't a place we can describe. It's a confession from physics that it doesn't know what's going on. What's truly unsettling is that the singularity isn't just a speck hiding in the middle. It might actually be a line depending on the black hole. In a rotating black hole, known as a Kerr black hole, the singularity isn't a point, but a ring. A circular region of infinite density surrounded by regions where space and time do things they have absolutely no business doing. Mathematically, those equations even allow for something wild. If you could somehow avoid the ring's singularity, you might emerge somewhere else entirely, maybe another region of space, maybe another universe. It's like saying that at the bottom of this cosmic pit might be a tunnel, not an end. Of course, there's a catch. You can't actually avoid the singularity. No known force, not even the strongest rocket or the most rebellious particle, can change its fate once inside. The pull of gravity increases endlessly, and the closer you get, the more extreme things become. The distances between your atoms shrink. The very concept of space stops behaving as space. And time, well, time gives up completely. From your perspective, you might still be moving forward, but there's no forward left to go. And yet, for all its hopelessness, the inside of a black hole might be the key to everything we don't understand about the universe. It's the ultimate testing ground where our two best theories, Einstein's general relativity and quantum mechanics, collide in a fiery argument that neither can win. Relativity describes the large-scale structure of space and time perfectly: planets, stars, galaxies. Quantum mechanics rules the microscopic realm: atoms, particles, and forces. But inside a black hole, both must apply simultaneously, and they can't agree on how. It's like trying to mix oil and water by sheer willpower. The result is theoretical chaos. Some scientists think this chaos hides a deeper order. They suspect that a future theory, quantum gravity, will one day replace the singularity with something more understandable, perhaps a region where space and time are quantized or grainy, like pixels on a cosmic screen. Others propose that the singularity isn't real at all, just a sign that we're missing a page in the universe's instruction manual. Maybe inside, instead of a point of infinite density, there's a bounce, a loop, or a bridge, a place where matter and energy are transformed, not destroyed. And then there's the philosophical side. What does it mean for something to exist if it's forever hidden from observation? The inside of a black hole might be real, but if no information can ever escape, can we truly say we know it exists? It's like a book you can never open, but insist is full of secrets. Physicists, being stubborn creatures, continue to theorize anyway. After all, not knowing has never stopped humanity from guessing. If you were somehow able to survive long enough to look around inside, ignoring for a moment the fact that you'd already been turned into atomic linguini, what would you see? Probably nothing recognizable. Light can't travel normally. Directions lose meaning. Space curves back on itself in every imaginable way. Some models suggest that as you approach the singularity, the universe might look as though it's collapsing in fast forward, all of existence being pulled into one final point. Others imagine bizarre mirages, flashes of distorted light from the outside universe stretched across strange geometries like smears of color on a warped mirror. It's eerie to think that every black hole hides one of these unknowable realms, scattered across the universe like sealed vaults of mystery. They sit there quietly, each one containing a secret that even the cosmos refuses to reveal. Inside them might be the key to understanding creation itself, or perhaps just the silence of physics admitting defeat. The inside of a black hole is, in many ways, the universe's greatest paradox. It's where existence continues beyond where existence is supposed to end. It's a region that is both real and unreachable, definable only by the limits of our imagination. And yet, in that unknowable heart, there's something deeply poetic. It reminds us that curiosity itself has a horizon, that there are places where knowledge stops and wonder begins. And so we stare from the outside, knowing we can never follow what falls in. The abyss holds its secrets tightly, and perhaps that's exactly as it should be. Because some mysteries aren't meant to be solved. They're meant to remind us that even in a universe governed by laws, there are still corners ruled by magic. At the center of every black hole sits a mystery so confounding that even the universe seems embarrassed by it. The singularity, a word that sounds elegant, almost graceful, yet hides a meaning that gives physicists nightmares. It's the point where all matter that ever fell into the black hole is crushed into an infinitely small region of infinite density. Every equation, every physical law, every comforting rule that has guided us through the cosmos so far melts, warps, and collapses here. It's the ultimate does not compute of the universe. Ask what's at the singularity, and physics says, "Don't talk to me until I've had coffee." The singularity isn't just strange, it's scandalous. It's the diva of physics, impossible to ignore, impossible to define, and constantly stealing the spotlight in theoretical debates. Everyone knows it's there, but no one really knows what it is. General relativity, Einstein's magnificent description of gravity, predicts it without hesitation. According to the math, once enough mass collapses under its own gravity, the curvature of space-time becomes infinite, and the equations describing it explode into nonsense. That's not poetic exaggeration. The math literally breaks. It starts spitting out infinities like confetti. Now, infinity might be a romantic idea in poetry, but in physics, it's the equivalent of a toddler scribbling over the last page of your homework. Infinity means we've reached the limit of what this equation can tell us. So while relativity confidently points to the singularity and says, "There it is," it also quietly mutters, "But don't ask me what's actually going on in there." Let's picture it in the simplest way possible. Imagine taking an entire star, millions of kilometers wide, and crushing it until it's smaller than a grain of sand. Then keep going, smaller than a speck of dust, smaller than an atom, smaller than a proton. Keep shrinking until there's no smaller left, and you still have all that mass packed into this nothingness. That's the singularity. Or at least, that's what relativity claims. It's not a point in space. It is the end of space. It's where the concept of where stops being meaningful. But physicists are not satisfied with that kind of answer. Infinite density? Infinite curvature? That's like saying the universe just gives up. So the hunt began for a better explanation. Enter quantum mechanics, the theory that governs the subatomic world, where uncertainty reigns and particles behave like both waves and solid things at the same time. Quantum theory and relativity usually stay in their separate lanes. Relativity for the big stuff, quantum mechanics for the tiny. But the singularity forces them into the same conversation, and it's not a polite one. Relativity says space-time is smooth and continuous. Quantum mechanics says it's fuzzy and jittery. Put them together inside a black hole, and they start arguing like rival chefs trying to cook in the same kitchen. The result? Theoretical chaos. The equations from both sides refuse to mix properly. producing contradictions that make even the most seasoned scientists sigh audibly in seminars. Somewhere inside the singularity, the quantum and the cosmic must merge into a single, unified theory, a quantum gravity that we have yet to discover. But until we do, the singularity remains an empty space in our understanding, a mathematical question mark wrapped in gravitational drama. And yet, the singularity is not all despair. It's also strangely hopeful. It's a clue, a cosmic breadcrumb leading us toward a deeper truth. Physicists suspect that once we figure out what really happens there, we'll finally understand how the universe began, because funny enough, the Big Bang, the birth of everything, might have been a singularity too. The equations describing the early universe look suspiciously similar to those describing the inside of a black hole, just running in reverse. It's as if black holes are the universe's way of recycling matter back into creation, or at least threatening to. Some theories even suggest that the singularity might not be a point at all, but a kind of bridge, a wormhole perhaps, connecting two distant parts of space-time. Others propose that the singularity is replaced by something new when quantum effects are considered, a Planck star, a region where matter bounces back before ever reaching infinite density. In this version, black holes might not destroy information but store it, waiting eons to release it in bursts of radiation. It's a tantalizing idea, though one that lives more in equations than in telescopes. Still, for all these elegant speculations, one stubborn fact remains. We can't see the singularity. Not directly, not indirectly. Everything inside the event horizon is hidden, sealed away by gravity itself. The singularity could be a dot, a ring, a loop, or something so alien that our vocabulary isn't ready for it. It could be pure energy. It could be geometry folded in on itself. It could even be an illusion, a side effect of equations breaking down at the edge of their usefulness. The truth might be less point of infinite density and more cosmic fog of unknown laws. If that sounds frustrating, you're not alone. Entire careers have been built on trying to peek into this darkness, to rewrite the math, to unify the big and the small. Every time someone thinks they've cornered the singularity with a clever new theory, it slips away again, like the universe whispering, "Nice try." And so the singularity remains, both the villain and the muse of modern physics, a gravitational diva demanding attention but refusing explanation. Perhaps that's fitting. The singularity represents not just the failure of our equations, but the limit of human comprehension. It's where understanding itself falls apart, crushed under the weight of infinite curiosity. And yet, that's what makes it irresistible. Because somewhere, buried in that impossible point, lies the next great revolution in science, the moment when we stop guessing and start knowing. Until then, we'll keep poking at the equations, keep imagining the impossible, keep trying to coax the diva out of her dressing room. Because if the singularity ever does reveal her secrets, she might just rewrite everything we think we know about the universe, from its beginning to its end. If you've ever watched two experts argue about something they're both right about, you already understand the struggle between quantum mechanics and general relativity. Each is brilliant on its own. Relativity governs the grand choreography of stars, galaxies, and space-time itself, while quantum mechanics handles the jittery, unpredictable dance of particles so tiny they make atoms look bloated. But bring the two together, and the universe suddenly sounds like a couple fighting over who gets to drive reality. Inside a black hole, that argument hits its peak. It's like putting a sumo wrestler in a ballet class. Both are talented, neither knows what to do with the other. To appreciate the mayhem, we need to step back and look at what makes these two theories so different. Einstein's general relativity paints the universe as a smooth, continuous fabric. Massive objects bend this fabric, and that bending is gravity. It's elegant, geometric, almost poetic. Quantum mechanics, on the other hand, says that everything, matter, energy, even space itself, comes in tiny, discrete chunks. Nothing is smooth. It's a universe made of jittering probabilities and flickering uncertainties. The laws of one describe cosmic order. The laws of the other thrive on chaos. They were never meant to share a room. But black holes don't care about theoretical boundaries. They are the ultimate intersection point, infinitely dense, infinitely small, and infinitely gravitational. They're where the large and the tiny collide. Inside a black hole, relativity insists space-time curves into a singularity. Quantum mechanics, horrified, screams that nothing can be infinitely small, because uncertainty won't allow it. You can't know both a particle's position and momentum precisely at the same time. So the idea of everything being in one single point, that's quantum heresy. So what actually happens? Nobody knows for sure, because we don't have a theory that can handle both gravity and quantum behavior at once. This is the infamous problem of quantum gravity, the holy grail of modern physics. It's the missing bridge between the cosmic and the microscopic. Every great physicist since Einstein has tried to build that bridge, and every one of them has so far ended up with splinters. Let's imagine for a moment what this chaos might look like. Near the singularity, the gravitational pull is so intense that even space-time itself starts to flicker. Quantum mechanics predicts that at extremely small scales, smaller than anything we can currently measure, space isn't smooth at all. It's made of tiny grains or loops of energy, constantly shifting and vibrating. Physicists call this the Planck scale, a realm so small that our best microscopes might as well be magnifying glasses made of cardboard. At that level, gravity itself might not be continuous. It could come in packets, just like light does. The smooth curve of Einstein's space-time could be replaced by a foamy, bubbling structure of micro-universes, popping in and out of existence like cosmic soda fizz. If that sounds insane, that's because it is. But it's also the kind of insanity physics needs right now. Several competing theories are trying to make sense of this quantum gravity mess. One of them, string theory, suggests that everything in the universe is made of unimaginably tiny vibrating strings, each with its own tone or frequency. In this view, particles aren't points, they're musical notes on the strings of reality, and gravity is just one part of the cosmic symphony. Elegant. elegant, yes, but there's a catch. String theory requires extra dimensions of space, sometimes 10 or 11 of them, curled up so small we can't detect them, so the price of elegance is living in a universe with more hidden rooms than a haunted mansion. Another idea, loop quantum gravity, takes a different route. It suggests that space-time itself is woven from finite loops of energy, like a cosmic chainmail. According to this theory, when matter collapses into a black hole, it doesn't get crushed into an infinitesimal point, but instead condenses to a smallest possible volume, a sort of quantum knot that resists further compression. In that case, the singularity wouldn't be infinite at all. It would just be the universe's tightest squeeze. Some versions even hint that when the knot snaps, it could create a new region of space-time, a baby universe budding off from the old one, the cosmos as the ultimate self-replicating organism. And then there's the idea of quantum foam, which might be the most mischievous of all. At the tiniest scales, space and time could be frothing with temporary particles, virtual pairs popping in and out of existence so fast they can't be directly observed. Near a black hole, this foam might become wild and turbulent, feeding strange quantum effects that ripple all the way out to the event horizon. In fact, Hawking radiation, the slow leakage of black hole mass over time, comes from this kind of quantum chaos at the boundary. Quantum uncertainty literally makes black holes evaporate, one particle at a time. What all these ideas have in common is a single humbling message. The universe is far stranger than our math can currently express. When we try to blend quantum mechanics with gravity, the calculations often blow up, literally giving answers like infinity times infinity. It's as if the universe is saying, "Nice try, but you're not ready yet." The laws that have guided us so well on human scales start to betray us in the extremes of density and smallness. And yet, there's something beautiful about this failure. The fact that our best theories clash so violently inside a black hole means there's something deeper underneath, a hidden structure, a missing piece, waiting to be discovered. The mayhem is not a flaw, it's a clue. It tells us we're standing at the edge of the next great revolution in physics. So inside that impossible environment where the massive meets the microscopic, the universe becomes both artist and prankster. It bends geometry, twists probability, and dares us to understand it. Somewhere in the quantum chaos, the rules of everything, space, time, matter, are being rewritten in a language we've only just begun to learn. Black holes are not just destroyers, they're laboratories. They're where physics stops behaving and starts hinting. In their heart, the sumo wrestler and the ballerina might not just coexist, they might actually be dancing to the same song, one we just can't hear yet. If the universe has one unbreakable rule, it's that nothing truly disappears. Energy changes form, matter transforms, stars die and become something else. But information, the underlying blueprint of all these things, is supposed to stick around. In physics, information is sacred. It's the fine print on reality's contract. You can burn a book, but in theory, every atom of ash, every wisp of smoke, still contains the information needed to reconstruct what was written. Maybe you'd need the patience of a cosmic librarian to do it, but it's technically possible. And then black holes strutted in and said, about that rule. Back in the 1970s, Stephen Hawking shocked the scientific world by proposing something that made the universe look like a messy data thief. According to his calculations, black holes aren't perfectly black after all. Tiny quantum effects near their event horizons allow them to emit faint radiation, what we now call Hawking radiation. Over time, this radiation causes the black hole to lose mass, slowly evaporating until it eventually disappears entirely. A beautiful, elegant idea. Except for one massive problem. If a black hole can vanish completely, then everything it ever swallowed, stars, planets, unlucky astronauts, vanishes with it. Not just destroyed physically, but informationally erased. That breaks one of the core principles of physics, the law of information conservation. The universe doesn't like losing data. It's the ultimate hoarder. Every particle's position, energy, and quantum state is supposed to be preserved, no matter what happens to it. So if black holes really delete information, the universe is breaking its own rules. And physicists hate when that happens. This dilemma became known as the black hole information paradox, and it's been haunting physics ever since. To understand how it arises, imagine throwing a library into a black hole. Every book, every word, every punctuation mark plunges past the event horizon. As far as the outside world is concerned, that information is gone. The black hole now just has a slightly greater mass and a slightly larger radius. But later, when it begins to evaporate through Hawking radiation, the radiation that escapes is completely random, thermal, with no trace of the original information. When the black hole finally vanishes, all the unique details that made up that library, everything that defined it, would be lost forever. It's like deleting the entire internet, then pretending the bits and bytes never existed. For quantum physics, that's blasphemy. Quantum mechanics insists that the universe is unitary, meaning that if you know the state of everything at one moment, you can, in principle, work out its past and future exactly. Erasing information destroys that predictability and replaces it with cosmic amnesia. For decades, physicists were split into camps. One that thought Hawking's calculations must be missing something, and another that feared black holes might genuinely be law-breaking anomalies in the universe's otherwise orderly system. As it turns out, Hawking's paradox forced some of the most creative minds in science to reimagine what a black hole actually is. Maybe, they proposed, the information isn't destroyed after all. It's just stored in disguise. Perhaps it's somehow encoded on the black hole's surface, smeared across the event horizon like a cosmic barcode. This idea, strange as it sounds, led to one of the most profound breakthroughs in theoretical physics, the concept of holography. The holographic principle suggests that everything happening inside a volume of space can be described by information stored on its boundary. In other words, the universe might be a kind of cosmic hologram, three-dimensional reality projected from two-dimensional information. If that's true, then black holes don't actually erase information, they just flatten it, compressing it onto their surface in a form we don't yet understand. The event horizon becomes a galactic-sized flash drive, storing every detail of what's fallen in, even if it looks lost from the outside. That may sound wild, but there's surprising mathematical support for it. In the 1990s, physicist Juan Maldatina discovered a model of the universe that perfectly demonstrated this principle: a holographic duality between a theory of gravity in 3 dimensions and a quantum theory on its 2-dimensional surface. This idea gave physicists new hope that information could be preserved even when matter collapses into a black hole. In this holographic view, the interior of the black hole isn't so much a forbidden region as it is a kind of compressed data file, one the universe can, in theory, unzip later. But just when everyone was feeling optimistic, another problem popped up. If information is stored on the event horizon and slowly leaks out through Hawking radiation, what does that mean for the experience of someone falling in? For that person, crossing the event horizon feels smooth and uneventful. But if all the information is actually stuck on the horizon, then something violent must be happening there, a kind of firewall that would incinerate anything attempting to cross. One side of physics said, that can't be true. General relativity says the horizon should be calm. The other side said, but quantum theory says it must be. And once again, the two pillars of physics started arguing like divorced parents over custody of reality. Hawking himself eventually changed his mind. In the early 2000s, he conceded that maybe information does escape, subtly encoded in the radiation, though no one yet knows exactly how. It's as if the black hole whispers out the details of everything it's eaten, photon by photon, over unimaginable timescales. The data isn't lost. It's just written in the world's most cryptic cosmic code. This ongoing puzzle has turned black holes into philosophical objects as much as physical ones. They force us to ask, what does it even mean for information to exist? If the universe truly is a self-consistent system, maybe nothing is ever truly gone, only transformed beyond recognition. Every collapse, every radiation, every end might just be another kind of record keeping. So while we may never retrieve that library we threw into the black hole, the universe probably still has it filed away somewhere, in a format we can't yet read. Perhaps every particle carries a whisper of its past, every photon a note of memory, all woven together in the silent bookkeeping of cosmic law. In the end, the information paradox isn't just about what happens inside a black hole. It's about whether the universe itself plays fair. And if history tells us anything, it's that the cosmos may bend the rules, but it never truly breaks them. It just hides the answers in places we haven't learned to look yet. For most of human history, a black hole was imagined as a one-way abyss, the universe's final garbage disposal. You throw something in, and that's the end of it. No returns, no refunds, no receipts. But in the 1970s, Stephen Hawking threw a mathematical wrench into that dark perfection. He discovered that black holes aren't truly black. They glow, ever so faintly, leaking energy into the universe through a process now called Hawking radiation. The irony is delicious. Something that swallows everything eventually starves itself. It's like the universe's strictest diet plan. Consume everything, then slowly fade away. To understand how Hawking came to this astonishing conclusion, we need to step away from the neat geometry of Einstein's relativity and wander into the jittery world of quantum physics. In that microscopic realm, emptiness doesn't really exist. What we call empty space is more like a restless ocean of energy filled with particles constantly flickering in and out of existence. These are virtual particles, tiny pairs that pop into being, one positive, one negative, borrowing energy from the vacuum for a split second before annihilating each other and vanishing again. It's like the universe's way of fidgeting when no one's watching. Now, imagine this happening right at the edge of a black hole. A virtual particle pair appears, one on the inside of the event horizon, one just outside. Normally, they would quickly reunite and cancel each other out. But here, gravity interferes with the reunion. The black hole's pull is so strong that one particle gets dragged inside while the other escapes into space before they can recombine. To an outside observer, it looks like the black hole has emitted a real particle of radiation. But nature always balances its books. The energy for that escaping particle has to come from somewhere. It comes from the black hole's mass. And that's the revelation. Every particle that escapes steals a tiny bit of the black hole's energy. Over billions, trillions of years, this adds up. The black hole loses mass, shrinks, and slowly evaporates. The universe's ultimate glutton, it turns out, is also on a countdown timer. But before you picture black holes exploding like cosmic popcorn, it's worth remembering that Hawking radiation is unimaginably faint. For a typical stellar mass black hole, say one with the mass of 10 suns, the temperature of its radiation would be a fraction of a microkelvin, colder than the cosmic background glow left over from the Big Bang. In other words, it's emitting less heat than a block of ice in outer space. The larger the black hole, the slower it radiates. Supermassive black holes could take numbers of years so large they make words like trillion sound silly, far longer than the current age of the universe, to even begin noticeably shrinking. Smaller black holes, however, are a different story. The smaller the black hole, the faster it radiates, because the quantum effects become stronger near a smaller horizon. In the final moments of their lives, such black holes might release massive bursts of energy, brief, brilliant flashes of radiation before winking out entirely. Some physicists have even speculated that tiny primordial black holes created just after the Big Bang could be reaching their end right now, evaporating with a bang somewhere in the distant cosmos. If that's true, The universe might occasionally flicker with the dying whispers of black holes that predate galaxies themselves. What makes Hawking's discovery so beautiful is its marriage of opposites. He used the mathematics of both general relativity and quantum field theory, two frameworks that famously dislike each other, to reveal that even the most extreme object in the cosmos can't escape quantum laws. The event horizon, once thought to be a clean boundary between inside and out, becomes a stage for subatomic drama. Space there isn't silent. It hums with quantum mischief, where particles constantly test gravity's patience. This insight turned the way we see black holes on its head. Before Hawking, they were eternal, dark, immortal endpoints of matter. After Hawking, they became transient, temporary. Even black holes, those titans of gravity, were mortal after all. It was a revolutionary idea that gave physics something priceless, a bridge, however fragile, between the quantum and the cosmic. But Hawking radiation did more than make black holes mortal. It also deepened the mystery. If black holes evaporate completely, what happens to everything they've consumed? Where does the information go? That question became the infamous information paradox, a puzzle that still sparks furious debate. Hawking himself originally believed that the information was lost forever, that the universe allowed a kind of ultimate forgetting. Later in his life, he reconsidered, suggesting that the radiation itself might carry subtle imprints of what fell in. If that's true, then Hawking radiation isn't just thermal glow. It's a whisper of the past, encoded in patterns too faint for us to yet decipher. One of the strangest implications of Hawking radiation is that black holes actually have temperature, and therefore entropy, a measure of disorder. That means they can be described using thermodynamics, the same rules that govern your coffee cooling on the counter. A black hole is, in essence, a cosmic thermodynamic object. It has energy, entropy, and temperature, just like a cup of tea, only, capable of devouring entire stars. This revelation led to the famous Bekenstein-Hawking formula, which links a black hole's entropy to the surface area of its event horizon. It's one of the most profound equations in modern physics, tying together quantum theory, gravity, and thermodynamics in a single elegant statement. And it's humbling too. Hawking radiation teaches us that nothing is truly static, not even the darkest things in the universe. Everything radiates, everything changes, everything fades. Black holes, those cosmic symbols of permanence, are slowly dissolving back into the fabric of space-time. Over unfathomable ages, the universe will dim as its black holes quietly evaporate into nothingness, releasing their stored energy in the softest of cosmic sighs. So, yes, black holes leak the impossible. They defy our intuition by glowing faintly with borrowed quantum light, each photon a tiny protest against eternity. Someday, far in the future, when the last star has burned out and only black holes remain, even those will fade away, leaving behind a silent sea of radiation, the faint echo of a universe that refused to keep its secrets forever. The mightiest eaters in the cosmos, undone not by hunger, but by the quiet patience of quantum physics. If the universe had a secret back door, a hidden hallway connecting distant corners of space and time, it would probably be a wormhole. For decades, physicists and storytellers alike have been obsessed with the idea. A tunnel through space-time, allowing you to zip from one end of the galaxy to another faster than light could ever dream of traveling. A wormhole is basically a cosmic teleportation rumor. Cool to imagine, terrible odds of survival. The concept comes straight out of Einstein's equations. In 1935, Albert Einstein and his collaborator Nathan Rosen noticed something peculiar. Their mathematical description of gravity allowed for bridges connecting two separate regions of space-time. These became known as Einstein-Rosen bridges, though today we've given them a far catchier name: wormholes. The term itself came later, inspired by the idea of a worm burrowing through an apple. The worm doesn't crawl around the entire surface, it just digs straight through, taking a shortcut. In theory, a wormhole could do the same for the universe, tunnel through the fabric of reality, turning light years into light minutes. Sounds simple. The problem is that, in theory, does a lot of heavy lifting there. Because while Einstein's equations allow wormholes to exist mathematically, they don't say anything about how to make one or whether nature ever bothered. Most of the wormholes predicted by relativity are incredibly unstable. The moment you try to send even a single atom through, the tunnel collapses faster than your Wi-Fi signal during a thunderstorm. The gravitational forces involved are so extreme that any ordinary matter would just turn into a smear of energy long before reaching the other side. So yes, wormholes might exist, but they're about as user-friendly as a paper bridge over a volcano. Still, that hasn't stopped physicists from trying to imagine ways to keep them open. One proposal involves something delightfully called exotic matter. No, not the stuff that glows under a black light at a rave. This kind of exotic matter would have negative energy density, meaning it would push gravity outward instead of pulling inward. Think of it as anti-gravity scaffolding, propping the wormhole open against its natural instinct to slam shut. Unfortunately, we've never seen exotic matter in the wild. Quantum theory allows for tiny, fleeting amounts of it, but not enough to keep a cosmic tunnel stable. It's like needing a mountain of antimatter to fix a hole in your socks. Even if exotic matter could exist in large quantities, traveling through a wormhole would still be a logistical nightmare. For one thing, time inside such a tunnel doesn't behave normally. Some models suggest that entering one end and exiting the other could land you not only in another part of the universe, but also in another time. That's where the time travel rumors come from. In principle, wormholes could connect different eras just as easily as different locations. But in practice, the paradoxes would pile up faster than unpaid parking tickets. If you used a wormhole to visit the past, would you erase your own reason for going? Would the universe allow such feedback loops, or would it self-destruct out of frustration? Many physicists suspect nature prevents such nonsense automatically. There's even a hypothesis called chronology protection, proposed by Stephen Hawking, which basically says, the universe hates time travelers. According to this idea, any attempt to create a time machine would cause the wormhole to collapse under quantum effects before you could step through. In other words, Reality enforces its own no paradoxes policy, no exceptions. But there's another twist to the story, one that makes wormholes more than just sci-fi fantasy. In recent years, some theoretical physicists have discovered surprising connections between wormholes and quantum physics. There's a growing idea that wormholes and a phenomenon called quantum entanglement, where two particles remain mysteriously linked across space, might actually be two sides of the same coin. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a theory nicknamed ER=EPR. Einstein-Rosen equals Einstein-Podolsky-Rosen. It suggests that every entangled pair of particles could be connected by a microscopic wormhole, tiny bridges of space-time linking quantum systems together. You can't travel through them, but they hint that space itself might be woven together by countless invisible tunnels. If that's true, then wormholes aren't just science fiction. They're part of the universe's architecture. Every quantum link, every entangled particle could be a miniature portal stitching reality into one connected whole. The large-scale wormholes we dream about might simply be the grown-up versions of these quantum bridges. The catch, of course, is that these quantum wormholes are far too small to travel through. Even a photon would have trouble squeezing in. The dream of flying a spaceship through one remains, for now, solidly in the imagination's jurisdiction. Still, wormholes persist as one of the most tantalizing possibilities in physics. They sit at the intersection of curiosity and absurdity, mathematically plausible, physically improbable, and narratively irresistible. They allow us to imagine a universe that isn't just vast, but cleverly interconnected, full of secret tunnels waiting to be discovered. Of course, the universe rarely hands out shortcuts. It tends to favor patience over convenience. Light, gravity, and time follow their laws with boring consistency, and wormholes, if they exist at all, might remain forever hidden behind those same rules. Even so, they serve an important purpose. They remind us that the cosmos is more flexible than it appears. Space and time aren't rigid walls. They're a fabric that can, at least in theory, bend, twist, and fold upon itself in ways that defy common sense. So, are wormholes real? Maybe. Are they traversable? Probably not. But as tools for imagination, they're invaluable. They challenge us to think beyond the visible, to ask whether distance is as absolute as it feels, or if the universe might have shortcuts it's just too polite to share. In the end, the wormhole is both a riddle and a metaphor. It represents humanity's eternal urge to find a faster way, a hidden path through impossibility. We may never build one, but the idea keeps us looking into the dark, wondering what bends behind the cosmic curtain. And that curiosity, more than any tunnel of space-time, is the real shortcut, the one that connects imagination to discovery. If regular black holes are cosmic vacuum cleaners, then supermassive black holes are entire real estate developers. They don't just tidy up, they own the block. These are the gravitational heavyweights anchoring galaxies, including our very own Milky Way. They're like the cosmic landlords, quietly pulling rent from billions of stars. Nothing happens in a galaxy without their gravitational signature stamped on it somewhere. A supermassive black hole isn't just an oversized version of the stellar kind. It's a whole different league of weird. While the black holes born from dying stars might weigh a few times the mass of our sun, the supermassive ones tip the scales at millions or even billions of solar masses. Their event horizons could stretch wider than the orbit of Mercury, maybe even beyond that. They sit in the centers of galaxies, invisible yet commanding, their gravity shaping the dance of entire star systems, like a cosmic metronome keeping the rhythm of the universe. Our own galaxy's central giant is a relatively modest specimen by cosmic standards. It's called Sagittarius A. That's pronounced A star, not A asterisk, unless you're trying to annoy astronomers. And it weighs about 4 million times as much as the Sun. It lurks 26,000 light-years away, hidden behind clouds of dust and gas, but its influence is unmistakable. Every star in the Milky Way's central bulge orbits around it, all held in its invisible grip. And while we can't see Sagittarius A directly, we've seen its fingerprints, stars whipping around it at breakneck speeds, some completing full orbits in just a few years. That's an entire sun, millions of times more massive than Earth, flinging itself around an unseen point of gravity like a cosmic tetherball. For decades, astronomers suspected something strange was sitting at the heart of galaxies. In the 1960s, they started detecting powerful beams of energy shooting out from the centers of distant galaxies, brighter than anything they'd ever seen. These were called quasars, quasi-stellar objects, because at first they looked like faint stars. But they weren't stars at all. They were supermassive black holes feasting on matter. As gas and dust spiraled into the black hole's maw, they heated up to millions of degrees, releasing torrents of radiation. Quasars are so luminous that they can outshine the combined light of 1 trillion stars. A single black hole, smaller than our solar system, powering an entire galaxy's worth of brightness. Now that is cosmic drama. It's ironic, really. The brightest things in the universe are powered by the darkest objects imaginable. But that's the beauty of supermassive black holes. They don't just destroy, they create spectacle. Their accretion disks, those swirling rings of matter being slowly devoured, glow with furious energy. Their magnetic fields twist and channel some of that material into colossal jets that shoot out for thousands of light years, beaming radiation across intergalactic space. If you're picturing something serene and elegant, think again. These are chaotic, blazing furnaces of gravity, hurling energy around like the universe's own fireworks display. Yet, for all their violence, supermassive black holes might also be responsible for bringing order to the cosmos. They act as the stabilizing centers of galaxies. Their immense gravity helps bind the stars together, while their jets and winds regulate star formation by blowing away excess gas. In that sense, they're both architects and enforcers. Too much gas, and they heat it up. Too little, and they draw it back in. Galaxies are not just random collections of stars. They're ecosystems, and at the heart of each one sits a black hole managing the balance. But how do these giants form in the first place? That's still one of astronomy's most tantalizing mysteries. Stellar black holes are easy to explain. A massive star collapses, and poof, a black hole. But supermassive black holes are too big to come from a single star. They had to grow fast, within the first few 100 million years after the Big Bang, which doesn't leave much time. Some theories suggest they started as seed black holes, maybe from the collapse of the universe's first giant stars, or from dense clusters of early matter, and then ballooned by consuming gas and merging with other black holes. Others think they might have formed directly from enormous clouds of primordial hydrogen, collapsing under their own weight, skipping the whole star phase entirely. Whatever their origin, once a supermassive black hole gets going, it's unstoppable. Every time galaxies collide, and yes, galaxies collide a lot, their central black holes eventually merge too, forming even bigger ones. These cosmic mergers send ripples through space-time, massive gravitational waves that can travel billions of light years. One day, we might even hear these galactic unions with future detectors, listening to the deep cosmic bass notes of black holes joining forces. Sagittarius A, our local landlord, is currently quiet, at least by galactic standards. It's not devouring much, which makes it relatively tame compared to the raging quasars out there, but every so often it burps. Telescopes have caught faint flashes and flares from its direction, likely caused by small clumps of gas falling in. Think of it as a sleeping dragon twitching in its dreams, but don't be fooled by its calm demeanor. If Sagittarius A decided to feast again, the night sky would be transformed. It could blaze brighter than every star in the Milky Way combined, turning our serene spiral galaxy into a glowing beacon visible across the universe. Supermassive black holes remind us that power in the cosmos doesn't always announce itself loudly. Sometimes it sits in silence, shaping everything without being seen. They are the gravitational hearts of galaxies, the engines of cosmic evolution, and the reason the universe has structure at all. Without them, galaxies might drift apart, star formation might run amok, and the universe would be a much duller place. So the next time you look up at the night sky, remember, every sparkling star, every gentle spiral of light is paying quiet tribute to an unseen ruler at the center. Supermassive black holes don't need to shout to command respect. They simply exist, massive, patient, and eternal, pulling rent from billions of stars, one orbit at a time. For every cosmic villain, there's a hero, or at least they're supposed to be. In physics, opposites tend to come in pairs, positive and negative, matter and antimatter, protons and electrons. So it was probably inevitable that someone would look at a black hole, this insatiable monster that swallows everything, and wonder, wait, what if there's something that does the opposite? Thus, the white hole was born, a cosmic mirror image that spits matter out instead of sucking it in. A white hole would be like a cosmic leaf blower, impossible to find, but definitely fun to imagine. On paper, the concept is simple. If a black hole is a region of space from which nothing can escape, a white hole would be a region into which nothing can enter. Matter and light could pour out of it, but nothing could ever fall in. It's the ultimate one-way street, but reversed. In theory, a white hole's event horizon would behave like a black hole's in mirror image. Instead of trapping everything, it would repel everything. To anything nearby, it would look like a dazzling, high-energy fountain of radiation and particles blasting outward into space. The idea of white holes came from the same mathematics that gave us black holes. In the 1960s, physicists noticed that if you take the equations describing a black hole and reverse the flow of time, you end up with something that looks just as valid, but behaves completely differently. Time reversal symmetry is a big deal in physics. Many fundamental laws don't care whether time moves forward or backward. So if the math for black holes works one way, flipping it should also describe something real, right? Enter the white hole, a theoretical twin that is the black hole's reflection across the time axis. But here's where the trouble starts. White holes, while elegant in math, make absolutely no sense in reality. They violate everything we know about how entropy, the measure of disorder, works. The universe moves from order to chaos, not the other way around. If black holes increase entropy by swallowing matter and mixing it up beyond recognition, white holes would decrease it by spontaneously spitting out organized matter from nowhere. It's like watching smoke gather itself into a neat little campfire again. The equations might allow it, but the universe probably wouldn't. Still, theoretical physicists are nothing if not stubborn, and they've found creative ways to keep white holes in the conversation. One idea is that a white hole could be the other end of a black hole, a sort of exit point in another region of space, or even another universe. In this picture, what falls into a black hole in one place might come shooting out of a white hole somewhere else, connected by a tunnel of warped space-time known as a wormhole. To an observer in that second universe, it would look like matter simply appeared out of nowhere, a gravitational magic trick. The notion is wildly speculative, but it's also deeply poetic. It suggests that destruction and creation might be two sides of the same cosmic coin. When something falls into a black hole, maybe it isn't gone, it's just been transferred, re-emerging from a white hole in a different corner of the multiverse. In that sense, black holes wouldn't just end things, they'd recycle them, turning cosmic endings into new beginnings. A star dying here might give birth to a star system somewhere else. It's an appealing thought. Nature as the ultimate recycler. Of course, there's no evidence for any of this. We've never seen a white hole, and every attempt to model one suggests it would be ridiculously unstable. Imagine a geyser blasting matter and energy into space for no reason. It would be like trying to keep a fire hose running without a water source. Whatever created it would have to continuously pump out material and energy, violating the laws of thermodynamics left and right. In short, white holes are the rebels of the physics family, mathematically neat, physically chaotic, and entirely hypothetical. But that hasn't stopped theorists from finding new angles. Some have proposed that the Big Bang itself might have been a kind of white hole. After all, the Big Bang was an explosion of matter and energy from a single, dense point that suddenly expanded into space, a lot like what you'd expect from a white hole. Maybe, the thinking goes, our entire universe is the inside-out version of another universe's black hole. If true, that would mean every black hole in our cosmos might be giving birth to new universes inside of it. A vast cosmic tree of creation branching endlessly. It's the kind of idea that makes you stare into space and quietly say, "Whoa." Others suggest that black holes might become white holes at the very end of their lives. According to some quantum gravity models, as a black hole evaporates through Hawking radiation, it might eventually bounce instead of disappearing completely. The collapse of matter could reverse, releasing everything it once swallowed in a final burst, a black hole's last breath becoming a white hole's first gasp. It's a wild possibility, but it ties neatly into one of the universe's favorite themes. Nothing lasts forever, not even darkness. Even if we never find a real white hole, the idea serves a purpose. It challenges us to test the limits of what our theories can describe. It reminds us that the universe doesn't have to follow our intuition. Black holes seemed absurd when they were first proposed to. Stars collapsing into invisible points sounded like pure fantasy. But now we've seen them, photographed their shadows, even detected their mergers shaking the fabric of space-time. Maybe white holes are just the next absurdity, waiting for a telescope sharp enough or a theory bold enough to prove them real. Until then, they remain the universe's most intriguing what if. What if time could flow backward? What if matter could be expelled instead of consumed? What if creation and destruction are merely phases of the same eternal cycle? White holes might be impossible, but they embody one of science's best habits. Its refusal to stop asking questions just because the answers sound crazy. They remind us that physics isn't just about equations and observations. It's about imagination, about wondering what happens when you flip reality on its head and ask, could the universe work in reverse? Maybe it can't. Maybe white holes are nothing more than elegant ghosts haunting the mathematics of space-time. But even as a thought experiment, they keep us looking both inward and outward, into the depths of black holes and into the beginnings of existence itself. After all, if the universe ever did invent a cosmic leaf blower, we'd probably still be too busy marveling at the mess it makes to care how it works. If the universe ever wrote a philosophy book, black holes would get their own chapter, probably the last one, because they're where every cosmic story seems to end. But endings are funny things in science. What starts as a conclusion often becomes a doorway. Black holes began as mathematical oddities, then became terrifying cosmic monsters, and finally, strangely, ended up being teachers. They are the universe's professors of paradox, forcing us to rethink everything we thought we knew about space, time, and the nature of reality itself. It's tempting to think of black holes purely as destroyers, those cosmic shredders that erase matter, light, and hope. But the more we've studied them, the more they've turned out to be the exact opposite. They are creators of understanding. Every time we've tried to figure out what's really happening inside or around one, physics has evolved. Einstein's theory of general relativity gave us the concept of curved space-time. Quantum theory gave us the rules of the subatomic world. But black holes are where those two worlds meet and argue, and in their conflict, reveal the cracks in our cosmic understanding. Think about how much they've already taught us. Without black holes, we might never have confirmed that space-time can literally bend, twist, and ripple. We might never have detected gravitational waves, the faint tremors that echo across the cosmos when two black holes collide. We wouldn't have known that information, matter, and energy are more tightly linked than we ever imagined, or that the vacuum of space itself hums with quantum potential. Every mystery they pose ends up being a lesson about how incomplete our picture of the universe still is. In a way, black holes are like mirrors. They reflect our limitations back at us. When we try to describe what happens inside them, our equations crumble. When we ask where their information goes, our logic ties itself in knots. And yet, in those failures, we find progress. Every paradox a black hole presents is a challenge, a cosmic riddle daring us to build better theories. Without them, we might have settled for comfortable ignorance, assuming the universe was simpler than it truly is. But black holes refuse to let us rest. They keep whispering, "You're not done learning yet." Their lessons extend far beyond physics. Black holes also remind us that the universe is full of contradictions that somehow coexist beautifully. They are the darkest objects imaginable, yet they give rise to the brightest phenomena, like quasars. They represent the end of time for anything that falls in, yet they may hold clues about how time itself began. They are silent, invisible, and patient, but also the engines of creation in galaxies across the cosmos. That balance, the way destruction and creation intertwine, isn't just poetic, it's universal. Even the way we've come to see them is a triumph of human curiosity. When the Event Horizon Telescope captured the first image of a black hole in 2019, a glowing ring of fire surrounding a dark center, it wasn't just a picture, it was a declaration. We'd managed to glimpse the unseeable. That image, blurry though it was, symbolized centuries of wonder, thousands of scientists, and the collective refusal of humanity to accept impossible as an answer. It proved that even in a universe full of darkness, curiosity can create its own light. And maybe that's the most profound thing black holes teach us, that curiosity itself is a force of nature. Gravity might pull matter inward, but curiosity pulls the mind outward. We are creatures made from stardust, orbiting an ordinary star in a small galaxy. Yet we've managed to imagine and even understand objects so extreme that they warp reality itself. That's not just impressive, it's humbling. Every black hole out there is both a cosmic mystery and a mirror of our desire to know. Of course, black holes also teach us humility in a more existential way. They remind us how fragile our notions of permanence are. Stars die, matter collapses. Even the greatest gravitational giants will, given enough time, evaporate into nothingness through Hawking radiation. In the far future, when the last star burns out and the universe is cold and dark, black holes will be the final monuments, slowly fading embers of cosmic history. Eventually, even they will vanish, leaving behind only radiation and silence. If that sounds bleak, it's also oddly comforting. The universe doesn't waste. It transforms. Every beginning ends, and every ending begins again, even if in forms we can't yet comprehend. Black holes also push us to ask the biggest of all questions. What is reality? If space and time can bend, if information can hide on the surface of an event horizon, if two colliding black holes can make the fabric of existence itself vibrate, then maybe our everyday experience of reality is just a calm patch on an ocean of much stranger possibilities. Maybe the laws we live by, cause and effect, up and down, before and after, are just local customs of a much weirder universe. It's possible that one day, long after we're gone, our descendants or our machines will understand black holes completely. They'll finally unify relativity and quantum mechanics, unlocking the true code of space-time. And when that happens, we might look back and realize that black holes were the key all along, the puzzles that forced the next leap of knowledge. Like teachers who never explained the answers, they just kept asking the hard questions until we were smart enough to solve them. Until then, we're left with awe. Because even if we never fully decode them, black holes will always remind us how far we've come and how far we still have to go. They are cosmic mysteries wrapped in gravity, sprinkled with chaos, and served with a side of existential dread. And yet somehow, they make the universe feel more alive, not less. Black holes show us that knowledge isn't about finding comfortable answers. It's about confronting the impossible and daring to understand it anyway. Even the darkest places in the universe still shine with curiosity. And maybe, just maybe, that's the point.